All right, so now we're just going to go to the next problem in the book, and we're going to right away encounter a difficulty. There's sort of a different kind of problem. So we're going to look at number 31 on page 407, looking at number 31. It says, find this volume of the solid generated by revolving the region bounded by the parabola y equals x squared and line y equals 1. Okay, so we can find that region. But then it says, revolved about the line y equals 1, and then a couple other lines, y equals 2, y equals -1. So it's revolving, but it's not revolving around an axis. So that makes the problem trickier, and it is called an off-axis revolution. All right, so that's one of the things we're going to do today. We're also going to do something called known cross-section. We're going to introduce a project today, all that's going to happen. But we're just going to start with this, the off-axis revolutions. So here's our problem. Here's our region definition, and we're revolving about these three lines. So you can refer to that in the problem. We're just going to start with part A. All right, so if I look at the region first, so let's start by looking at the region. So I have, let's draw a coordinate plane here. And we got y equals x squared, so I'm going to draw it kind of low to the ground here. So here's y equals x squared. All right, so here's the point. And then the other line we have is the line y equals 1. So y equals 1 is going to go across like this. So of course it continues out like that, but I'm not going to draw it. So here's y equals 1. And also, by the way, that's the point, x equals 1. We can figure that out easily enough. Now, so let's consider this first strange idea that we're not going to revolve around the x-axis or the y-axis. We're going to revolve around that line, y equals 1. So this is our axis of revolution, is y equals 1. So what's the shape going to look like? So, well, the shape's going to flip up this way. So we're going to have a parabola up here. So we're going to have a football or an almond, if you like. Up here, but it's above the x-axis, so it's like rotated like that. So how does this change the math if we're not on the axis anymore? Well, not terribly a lot. So what happens is, we're essentially, this is what I would call a simple shape because it does not have a hole through it. It's simple because it has no hole. All right, so that means we're going to use the method of disks, not washers. The difference between a disk and a washer is a disk has no hole in it and a washer does. So it basically just has, our ith volume element is just a disk like this. So our v sub I is going to be pi r squared h. So it's always good to come back to this ith volume element, but you're going to find we're going to develop a formula and we won't need to come back to it every time. So in this case, but it's always good to think about, what is the radius? That's the whole key to these. What is the radius? Well, what I usually do to think of like what that radius is think about where the radius begins and ends. So let's just say I look at a blow up of that cross section, or at least a less messy version of that cross section, okay? So we have the line y equals 1 here, and well, I guess it's sort of putting it on the top is a little hard to see exactly what it is because it would change the function. So let's look at it at the bottom. All right. So because at the bottom, I know what this function is down here. It's y equals x squared, right? This one up here is like y equals 1 minus x squared or something, but I don't want to have to think about that. So because the radius of the disk I can also find below, and it's just easier to find. It's the radius down here. So where does the radius begin and end? The radius begins at y equals 1 and ends at the y equals x squared. So that means that the radius is 1 minus x squared. All right? So that means in terms of my v sub I here, I have v sub I equals pi, we'll put 1 minus x sub I squared, and then our height is going to be, since we're integrating with respect to x, it's delta x. That's the width of the disk, so it's the height of the cylinder, delta x. All right, so then our volume becomes the limit as x approaches infinity, that stuff. Oops, that's not a v. The volume is, I'll keep the pi out like we normally do, and I'll have the integral. Now I'm going to do a funny thing with this 1 minus x squared since I forgot to put the square on it, right? It's r squared, so we need squared here. So I'm going to do this funny thing. I have a reason for doing this, but it won't be obvious yet. Instead of writing 1 minus x squared, since this is squared, I'm really I'm really taking the absolute value. I mean, I could have gone down here and said the radius is the absolute value of 1 minus x squared, which means I can reverse the direction of subtraction and make it x squared minus 1. And you'll see in a bit why I want to do that. Squared dx. So that's my integral. Okay? Now, what about the limits on the integral? This is dx, so the limits are going to be x coordinates. All right, that's just a general principle you want to know. If I have dx, limits are going to be x coordinates. What are my x coordinates? Well, the x coordinates go from -1 to +1. So those are my limits, -1 to +1. All right, so now I've got my integral and I can do my integral. But before I proceed, I'm going to remember that idea that we had from 2D shapes, that I can take advantage of symmetry. This shape is symmetric with respect to the x-axis. So that means that actually all of these problems that we're going to do for this particular problem, they all have symmetry. So I want to remind you that we can use symmetry. So what I'm going to do is right away rewrite this integral as 2 pi times the integral from 0 to 1 of x squared minus 1 squared dx. And that's going to net us a huge savings in work by having a 0 here and not having to deal with that -1. It's going to make it much easier. All right, so then what do I have? I have, so we'll go ahead and square out the binomial. 2 pi integral 0 to 1, x fourth minus 2x squared plus 1 dx. I guess I don't need the parentheses there, but I put them anyway, so there. So this is going to be x fifth over 5 minus 2x cubed. I mean, you could finish this on your own if you want, but here you go. You can just watch too. We're going from 0 to 1, and then I have 2 pi times 1/5 minus 2/3 plus 1. I think I'm only going to put this minus 0 once, so we can get out of the habit of writing it. Because the lower thing is 0, the lower limit is 0. But you know, like I'm always hesitant to do that because you can't forget. You can't forget about that lower limit. You acknowledge that we know we're going to get 0 in all these terms. If we'd had a constant term here, we couldn't do that. All right, so then what do we got? So that's going to be 2 pi. So we're going to have 3/15 minus 10/15 is -7/15 plus 15/15 is 8/15. So we're going to be times 8/15, and we get 16 pi over 15, and that's that one. All right, we'll do part B next, off-axis revolutions. Here we go.